Welcome to the third screencast for Chapter 9, dealing with gases. We're going to start this screencast by looking at example 10, which deals with how a car's airbag works. So what a car's airbag needs to do is it needs to fill up with gas very, very rapidly so that if you're in a collision, the airbag is going to be softer, if you will. It's going to decrease the force that's exerted on you when you are moving into the car's dashboard or windshield, and so it's going to provide you at least some protection from the crash. One way to do this is to use the decomposition of a compound known as sodium azide, which when it decomposes, and it does this pretty rapidly, makes sodium solid and nitrogen gas, and it's the nitrogen gas that is going to fill up the car's airbag. In this particular case, the airbag has a volume of about 45.5 liters, and typically these fill with gas at a pressure a little higher than atmospheric pressure, not too much higher, or the airbag is so rigid that it's actually almost as bad as colliding with the dashboard or the windshield. And it's good if the gas in there is not at too high a temperature so it doesn't burn you as well. And so it's going to be at not too much above room temperature typically. And the question is, how much sodium azide is needed to provide the appropriate amount of gas for this process? So let's work our way through this problem. We're going to note that even though we're trying to find the amount of sodium azide, all of the information in the problem gives us information about N2 gas. And so for nitrogen, since it's a gas, what we know is that the pressure of the gas times the volume of the gas is equal to the amount of gas in moles times the ideal gas constant times the temperature, i.e. the ideal gas law applies here. We know the pressure, 130 kilopascals. We know the volume, 45.5 liters. We are trying to find the number of moles. The ideal gas constant is a known quantity, and we know the temperature, 30 degrees Celsius, but of course we would like to find it in, or we need to use it, I should say, in Kelvin. So we can solve this equation for the number of moles N. It's equal to PV over RT. And so let's plug in our values and see what we get. The pressure is 130 kilopascals. The volume is 45.5 liters. The ideal gas constant is 0.08206, and the units for this are liter atmospheres per mole Kelvin. And then the temperature, 30 degrees Celsius plus 273, gives us 303 Kelvin. And liters cancels, Kelvin cancels. Moles is what we're trying to find, and we have 1 over moles, so that's going to be good. But we have kilopascals and atmospheres for our pressure, so we're going to have to do a conversion, and there are about 101 kilopascals. It's actually 101.325 if you want to be more precise. Kilopascals per 1 atmosphere. So we can convert from kilopascals into atmospheres, and then the atmospheres will cancel. And if we plug in all of our numbers, what we end up with is 2.38 moles of nitrogen. That is the amount of nitrogen that fills up the balloon, the airbag, under these conditions. Now we're actually trying to find the amount of sodium azide, so we're going to have to convert our number of moles of nitrogen into an amount of sodium azide, and what we know is for every 2 moles of sodium azide that react, 3 moles of nitrogen gas are produced. So we have 3 moles of N2 that come about from every 2 moles of sodium azide, NaN3. Moles of N2 will cancel, so 2/3 of 2.38 works out to be 1.59 moles of sodium azide. And then note, this is actually a perfectly acceptable answer because this is actually an amount of sodium azide, but we're typically going to have to weigh this out in grams. So if you want to convert from moles to grams, there's 65.0 grams in 1 mole of sodium azide, and that works out then to be about 103 grams, let's make that actually grams, of NaN3. So either one of these is a perfectly acceptable answer. Okay, one more example in this screencast, and this is a reaction that might be demonstrated for you when you're physically in class, but we can have a bubble that contains butane, and if we put a spark to it or match to it, it will burn. And it's more dense than air gas. It sinks and it burns when there's oxygen around and makes carbon dioxide and water. So several questions here. What's the density of the butane? What's the molar mass of the butane? And that might help us find out the formula. And then what volume of oxygen reacts with the butane and what volume of CO2 is produced. So let's do these one at a time. First of all, what is the density of the butane? Well, this one's pretty easy. Density is simply mass over volume. And the mass of the butane gas is 0.294 grams. And the volume of the butane gas bubble is 125 milliliters. And we can, of course, just leave this in milliliters. That would be perfectly fine. And if we do this, that what we end up with is 0.00235 grams per milliliter. Now notice the density is really small compared to normal densities we've seen for liquids and solids, which is not too surprising. And of course, if we would like to do things where the numbers aren't quite so small, and sometimes we do this, we could convert milliliters to liters, and we'd have 2.35 grams per liter as the density, and either one of these is perfectly fine for our result. Okay, second question, determine the molar mass of the butane. Well, what is molar mass? Molar mass is, of course, just simply grams per mole. Now, if we knew the formula of butane, which of course you can Google and look up, then we could just determine the molar mass from the formula, but often we may not know that. We're trying to determine it, and here's some data that could help us. So to find the molar mass via grams per mole, the grams is known, 0.294 grams, so this is known, which means what we need to find is the number of moles. And we've seen how to do this before. The number of moles for a gas is PV over RT. So let's figure out the number of moles for butane. Pressure is 0.985 atms. Volume is 125 milliliters. This we do need to make into liters because we are going to be using the gas constant that has units of liters and atmospheres and moles and Kelvin. So 0.08206 liter atmospheres per mole Kelvin. And then the temperature of 23.8 degrees Celsius. When we add 273.2 to that, we get 297.0 Kelvin. And plugging that into our equation, or into our calculator, what we end up with, and note that atmospheres will cancel, liters will cancel, Kelvin will cancel, 1 over moles gives us moles, and we have 0.00505 moles of butane. And then the molar mass is simply the number of grams, 0.294, over the number of moles, 0.00505, and that works out to be 58.2 grams per mole, which answers the question. Now, if we had more information like mass spectrum of butane or percent composition, we could finish the problem and get the molar mass, and get the formula, and it turns out that butane has a formula of C4H10, which corresponds to 58.2 grams per mole. Okay, so our last two parts of this problem. What's the volume of oxygen that reacts with the butane, first of all? And two things. One is we'll need the balanced chemical equation, and this would be something you could do. Butane C4H10. It's going to react with oxygen to make CO2 and H2O when it burns. And here's the balanced chemical equation. Should be pretty straightforward for you to do. And now note the volume that reacts with of oxygen that reacts with the butane. Well, the moles are in a 2 to 13 ratio, but what about volume? Well, note something, and that is that the relationship PV equals nRT allows us to relate moles and volume. They're directly proportional, providing, of course, that the pressure and the temperature are constant. So let's say that that's the case. We'll be doing this at pressure and temperature being the same for both. And what that then means is if we're trying to determine the volume of oxygen that reacts with the butane, we can simply say we have 125 milliliters of butane, C4H10, and the 125 milliliters of butane reacts with oxygen in a 13 milliliter of oxygen to 2 milliliter of butane ratio, because it's the same ratio, 2 to 13, as moles, because volume and moles are directly proportional to each other. Milliliters of butane cancels, and 13 times 125 divided by 2 works out to be 812.5 milliliters of oxygen, and of course providing pressure and temperature are the same for both, which is what we're stating is the case. Now, what if we're doing the volume of CO2 that's produced? And once again, if we have pressure and temperature being the same, so P and T same for both, then what we're going to have is 125 milliliters of butane times 8 milliliters of carbon dioxide for every 2 milliliters of butane, same ratio by volume as it is by moles, and that works out to be 500 milliliters of CO2, providing the pressure and temperature are the same for both. All right, so that's it for this screencast.